thank you very much for the invitation. It's always great to get down here and see my friends and the fantastic work they're doing. Instead of the wonderful specific talks we've heard so far, I want to step back and talk about the general problem of turbulence and the need for wind tunnels. As I'm sure you know, turbulence is the most unsolved problem in all of classical physics. It's much harder than simple things like relativity or quantum mechanics, and that's why it hasn't been solved yet. And as I'll try to demonstrate, and as I'm sure you already know, it's everywhere. This is my favorite planet, and it's hard to take a picture of it without showing turbulence. You may recognize this coastline. There was supposed to be a video there that would show the water temperature off the east coast of Brazil as a function of the date. And the red of color corresponds to warm tropical water and the blue to cold water. And of course, the water motion is highly turbulent, as you would expect. The largest planet in the solar system. And if that doesn't make you think of vortices, then there's not much I can say. Well, I'm not able to get that video working either, but when you see time lapse of Jupiter, of course, it's completely surrounded by these zonal flows and vortices. We were talking earlier about the importance of Reynolds number, previous speakers were, and on Jupiter, 1 degree of latitude on Jupiter and the characteristic velocity differences correspond to a Reynolds number of 10 to the 13th. So that organized vortices are known to exist up to at least to a Reynolds number of 10 to the 13th, which is higher than most engineering applications on this planet. I'm sorry, my videos aren't working. Well, we've talked a little bit about turbulence models already at the workshop. The difficulty at high Reynolds number, the types of Reynolds numbers that engineers are forced to confront, is that at large Reynolds number, the fundamental equations, the Navier-Stokes equations, are a singular perturbation problem. In practice, that means that nobody knows how to make an approximation that gives approximately the right answer. People for about a century have been coming up with models for turbulence, Prandtl's eddy diffusivity, the so-called Reynolds average Navier-Stokes equations. Of course, Navier-Stokes equations literally are the exact equations of motion as far as we know, but Reynolds average, as you know, means taking a time average and modeling the influence of the small scale eddies. One can do direct numerical simulations on the large eddies, but at high Reynolds number, because of the spectrum of turbulence, it's not possible to model to calculate the small eddies, and so the effect of the small ones on the big ones has to be modeled. And those models always involve adjustable constants. all turbulence models at high Reynolds number must of necessity tune their results to nearby wind tunnel data points. Don Coles at Caltech has called these numerical approaches French curves, where the wind tunnel data points the models are tuned to adjust nearby wind tunnel data points. Well, if you have a nearby wind tunnel data point, that's great. You don't have to interpolate or extrapolate very far, and the chances of being approximately right in the simulation are good. But if the wind tunnel data points are far apart, or if the physics in between the points is not smooth, and I'll give an example of that in a minute, then even a French curve is very dangerous. I mentioned direct numerical simulation. This is solving the same equations as God, and it's hard to argue with that. The difficulty, of course, is that at high Reynolds number, the turbulent eddy spectrum is too wide to handle. And to give you some idea of that, for classical Kolmogorov turbulence, the number of degrees of freedom n goes like Reynolds number to the 9th power. And these are just spatial degrees of freedom, not including time. So if the flight Reynolds number was approaching 100 million, 10 to the 8th, then the number of degrees of freedom is 10 to the 18th. Good luck solving that. The world's largest computer running for, say, a century cannot solve that. And so we're obliged, in order to address real engineering problems at high Reynolds number, to use something else other than direct numerical simulation. I think currently the world record for direct numerical simulation is something like Reynolds number 10 to the 4th or so. And if you're working on a problem at higher Reynolds number, then you have to do something else. Now, if you wait a while, Moore's law says that every 18 months computer capabilities double. But I figure this isn't going to be good enough in my lifetime, and it may not even be good enough for the lifetime of the students. You have to wait a while for computer power to be able to handle Reynolds numbers of 10 to the 7th or 10 to the 8th with full direct numerical simulation. I love direct numerical simulation. It's the brute force approach, but it just can't get to high Reynolds number. So I want to give 3 examples of surprises that wind tunnels and water tunnels have been crucial in discovering, and to illustrate also the danger of having too much confidence in a French curve that's spanning data points that are too far apart. The first is a flow around a very simple object, the rectangular cylinder. This is a plot from a book by Horner, who was a Messerschmitt designer during World War II, and he came to the States afterwards. And he published really almost the Bible for aerodynamicists on drag, fluid dynamic drag. And I want to draw your attention. I want to draw your attention to this curve in this plot of the drag coefficient versus the chord to thickness ratio for a rectangular cylinder. So this is a 2-dimensional object with a thickness T and a chord C and the flow as indicated. And if there are just a few data points that are plotted, and a French curve was used to draw the smooth line in between. Remember the shape of this curve. It goes up to about 2, and it asymptotes down to about 1. And it's more or less monotonic in between. Nagaguchi et al. Back in 1967, and later Bierman and Truman measured the data in the top part of this curve This is a plot of, again, drag coefficient versus the same chord to thickness ratio, but using Bierman and Truman's notation. The lower curve, by the way, is just the pressure coefficient on the backside, the base, as a function of this aspect ratio. And compare this curve with the previous curve that was more or less monotonic. Instead, we have the Matterhorn here. There's this giant mountain that was missed in the original measurements, or I should say, the original measurements in the French curve. At an aspect ratio of about 0.62, the drag coefficient goes all the way up to 3 in a very narrow spike. And it comes back down just as fast. Let's talk a little bit about the physics of that. If the aspect ratio is small, so the chord dimension d is small compared with the thickness, the boundary layers, of course, separate at these sharp edges for any Reynolds number much above 1. Can you hear me okay in back? I can't tell if I'm too loud or too soft. So you're guaranteed of getting one separation point on a side and no reattachment because the body is so thin. You can't be too thin or too rich or have too much chocolate. If the body is long, though, the initial separation is guaranteed to reattach. And of course, you have a second separation at the trailing corner. So topologically, these two flows are apples and oranges. They're completely different. If you draw a smooth French curve from the results for this flow to the results for this flow, you're asking for trouble. And in this example, you got it. Here's some images of the flow from Bierman and Truman when they vary the aspect ratio. If the body is relatively thin, the flow separates, and the vortices on the lee side roll up fairly far away. But at the critical aspect ratio of about 0.6, look how close that lee vortex is to the base of the body. Vortex cores have very low pressure, and if the vortex core is very close to the surface has very low pressure. And if the surface is the lee surface, the drag is very, very high. Here's another picture from Norberg showing at the critical aspect ratio how incredibly close the vortex is when it rolls up. The flow separates and it almost reattaches, but not quite. It's almost like incipient reattachment. And this magical condition produces the lowest possible base pressure and very high drag. Normally, aerodynamicists aren't interested in drag. You're trying to avoid it. But if you're designing parachutes or aeroballistic decelerators for entry into the Martian atmosphere, you'd like to have a very high drag coefficient. And discontinuous things happen, in this case to the base pressure, right at the critical aspect ratio. So that's one example of counterintuitive results where it's dangerous to interpolate. I'd like to give a second example, and this is from a water tunnel, or actually not a tunnel, but a water tank. And it's a simple experiment where there's light fluid. Maybe I'll just point at the board. There's light fluid, fresh water, floating on top of salt water, and a jet of salt water is coming up from below. And that turbulent jet is impinging on this thin stratified interface. And the question is, what is the entrainment rate across this thin interface due to this impinging turbulence? And how does it compare in the case A, where the jet is vertical, and case B, where the jet is tilted just 15 degrees, 15 degrees, and precessed with a rotating nozzle block down here? And my student, Aline Cotel, did these experiments. A sheet of laser light and acid base and a pH indicator that fluoresces so that when the jet impinges on the interface and causes mixing, you see the fluorescent mixed fluid. This is the plot of the dimensionless entrainment rate, how fast that interface rises due to entrainment across it, as a function of the strength of the stratification as measured by a parameter called Richardson number. And the upper data set with the open symbols corresponds to the vertical jet. And the X's in the lower data set correspond to the precessing jet. If you think about it for a little bit, and I guess I should have asked you ahead of time, which of those two cases would you anticipate would have the greater entrainment rate? The precessing jet, where the jet is swirling around, or the case where the jet is just vertical? I think when I've asked previous audiences this question, the overwhelming majority thought the precessing jet would have greater entrainment rate. In fact, it goes just the opposite, and not by a little bit. This is a logarithmic scale, and at the highest Richardson number we tested, the difference between the vertical jet and the tilted jet is over a factor of 100. Just a little bit of motion changes the entrainment rate by a factor of over 100, and it lowers it counterintuitively. Well, when you stumble across something that's interesting and you're an engineer or a scientist, the rational thing to do is to pursue that idea and propose a hypothesis and then throw tomatoes at the idea, see if you can chew down your theory. And the theory that we had proposed is that what mattered was the stationarity of a vortex near the surface. We believe that accounts for the difference in those entrainment rates. If that theory is right, then the question is, does that work if the surface is a solid body rather than a stratified interface? So imagine you had a vortex near a solid wall. Would the ratio of the rotational speed W to the translational speed V affect the physics? That's a measure of the stationarity, that intrinsic velocity ratio. And I had another bright student, Greg Ball, who pointed out that in the von Karman, the temporal von Karman wake, the vortices are known to be quasi-stable. And of course, in order to make a vortex stationary, you have to somehow hold it in one place. And so we got a piece of precision corrugated roofing material. I think they gave it to us. And we put a vortex generator in front of each trough in that roofing material and put it in our water tunnel. Here are a couple different ones that were made later on with some stainless steel of two different wavelengths. And you see here on the left some vortex generators, one in front of each trough. And here's a wavy wall painted black with 3 vortex generators on the left. And what was found was, just as we had suspected, if you put a vortex right over the crest of one of those right over one of those troughs, you could get the flow to become laminar. Unfortunately, we were only able to get it laminar over about half of a wavelength. This is a plot of the turbulence intermittency measured by a hot film probe as a function of position across the one cycle of the wavy wall. But Instead of this pattern, which is what we sort of anticipated, we got a pattern that was much more like this in the flow. This is a famous Kelvin's cat's eye pattern. If you have a row of vortices of equal sign, point vortices of equal sign and strength, equally spaced, then you get this pattern. And the significance of this pattern, as we'll see when we compare it with a different kind of shear layer, is that the lines in bold, the dividing streamlines or separatrix, don't allow any entrainment. So there's no flux from the outer flow into the inner flow across these streamlines, except for just very minimal amount of laminar diffusion. There's no turbulent entrainment. This has been observed before in the fourth shear layer back in the early 80s by Oster and Wignansky, and we now think that we see it in a boundary flow. The upper picture is the von Karman wake that we thought we were going to get. This is Olivia Dawson's sketch of what the flow field looked like, and this is what it most resembles, Kelvin's cat's eyes. And I'll just say one other thing that I should mention, that when we build a small wind tunnel model, an airfoil, and we put such streamwise vortices in the flow, we're able to, and hold them stationary, we get much higher stalling angle of attack and much higher lift coefficients than even if the wavy wall wasn't there and all we had were conventional VGs. So there appears to be some big advantages aerodynamically to streamwise vortices when you make them stationary. The physics are completely different. And if you have an incident laminar boundary, turbulent boundary layer, and you add in these strong stationary vortices, the boundary layer becomes laminar over at least half of the wavelength. And of course, as was mentioned earlier, at flight of Reynolds numbers, the drop-in skin friction is huge. If you can go from a turbulent to a laminar boundary layer, it's about a factor of 10. We've demonstrated laminar wall heat transfer at the bottom of the trough by adding these vortices, and we're going to be conducting further experiments in our big wind tunnel to see if the high lift performance continues to look good at high Reynolds number. Let's see if I can get this movie to work. Yeah, none of these movies are working, I'm sorry to say. Well, let me go back. I would have shown you a movie from the famous Brown-Roshko experiment of a shear layer. This differs from the Kelvin's cat's eye in that the vortices are not equally spaced. And because they're not equally spaced, they pair and grow and entrain, and the thing grows like crazy. Here the flow is from right to left, and this is a chemically reacting shear layer showing where the mixing is occurring. The red stuff is produced when the two streams mix. And that leads me to the third topic, which is mixing and demixing in two-phase flow. This is an experiment from Kouchis, Vahani, and Dimatakis, yet another wind tunnel experiment. Well, actually, this is still water tunnel, I'm sorry. In fact, it's my old water tunnel at Caltech. And they interrogated the mixing in a shear layer along that argon ion laser beam. And a model that we were interested in pursuing is one in which it's a very simple model in which vortex cores are composed of a single composition, and the two streams have these Taylor layers, and in which there's some mixed fluid, although in liquids not very much because the diffusion is so slow, and the vortex cores, the so-called bachelor layer mixing. And the take-home message is that in this cartoonish model, the vortex cores are supposed to have a single composition and sharp edges. And rather incredibly, as you'll see, that model seems to work. Here are a couple of images from Kuchis-Vahani and Dimitrakis at low Reynolds number below the mixing transition. And you see color coding here. So pure red corresponds to fluid on one side of the stream, pure blue from the other stream, and mixed fluid is either green or yellow. But in water, diffusion is so slow, there's almost no mixed fluid below the mixing transition. Here you see two vortices on their honeymoon, and they're uniting to form a new larger one. This is what happens above the mixing transition. Again, the color coding, there's pure red fluid below, pure blue fluid above, and here you see a vortex core with more or less a single composition of sort of greenish fluid. And the shocking thing is that the vortex has the same more or less green color all the way to the edge. I mentioned earlier the idea of eddy diffusivity and gradient diffusion. If those ideas were right, on the red side of the layer, you would expect to progressively go from red to yellow to green to finally blue. You see that doesn't happen at all. This is what the probability density function or histogram of the scalar concentration looks like in water. The left image is below the mixing transition, and you see pure fluid on one side of the layer, pure fluid on the other side of the layer, and nothing in between. This is composition from 0 to 1 of one of the conserved scalars. And this is distance across the layer. This is on one side of the layer, and this is on the other side. The right image shows the probability density function above the mixing transition. Again, you have pure fluid on one side and a delta function for the pure fluid on the other. But this mixed fluid in the middle, and the significant thing is that the ridge of mixed fluid here is not going along the diagonal, but it's going in this direction. There's a single predominant composition. To first order, the vortex cores are uniformly mixed. One more look at the probability density functions. This is below the mixing transition, and then above the mixing transition, you get mixed fluid in the vortex cores. And here's the amount of mixing, the dimensionless amount of mixing is a function of a Reynolds number, and the mixing increases by a lot. In fact, these data, the triangles are from Kuchis-Vahani and Dimitrakis, and the other data are all too high. They need to be shifted down by about that amount. Both they and I made a mistake in the calibration. So in water, at the mixing transition, the mixing increases by orders of magnitude. In gases, it's only about 20%. So in turbulence, the mixed fluid is in the vortex cores. But something magic happens when you go to two-phase flow. And in fact, exactly the opposite. The Stokes number is defined to be the ratio of the particle inertial response time to some flow acceleration time, tau p over tau a. If we have a vortex sitting here with a rotation period tau v, then the appropriate acceleration time of the flow is just the vortex rotation period. If we have flow approaching the leading edge of a wing or a pitot tube or a horizontal stabilizer with an osculating circle leading edge radius of curvature r naught, then the flow acceleration time is r naught over u, where u is the approach speed. As we'll see in a second, if the Stokes number is greater than 1, so the particle time is greater than the acceleration time, then the particles cannot change direction, and so they slam into the surface. That occurs when tau a is relatively small, or when the leading edge radius is small. The first parts of an airplane to ice up are the smallest parts, like horizontal stabilizers and antenna and wings, and pitot tubes. Things with a large radius of curvature have a lower Stokes number, and they ice up more slowly. Crow et al. Back in the 80s did an experiment where they set up a shear layer, so there's high-speed flow here and low-speed flow here, and they seeded the flow with particles. And what they found was if the particles are very tiny, that is to say the Stokes number of the particles are much less than 1, of course the particles follow the flow, and if a streamline curled around like that, so did the particle. The particles were along for the ride. The other limit, the Stokes number much bigger than 1, the particles are totally insensitive to velocity fluctuations. They're giant bowling balls, and of course they just keep going in the same direction, totally insensitive to the flow. The interesting thing is, of course, when the relevant parameters of order 1, if you have an intermediate-sized particle, they get centrifuged out of the vortex cores. Remember we saw earlier that in turbulence, the mixed fluid is in the vortex cores. That is, unless the flow is two-phase. Here's an experiment by Yang et al., the same group at Washington State University. They had a splitter plate in a wind tunnel and a sheet of laser light, and they forced the flow with an acoustic speaker to phase lock the shed vortices, and they injected particles here. So this is a wake. You notice the two streams have the same speed on either side of the splitter plate, so it's a wake. And they seeded the wake with particles. Watch what happens to the particles. Here is what the flow looks like without any particles, and you see, of course, the vortices. If the Stokes number is much less than 1, because the particles were put in the wake, they're still in the vortices at this downstream station. There's a vortex there and one there. In fact, this is taken at some phase where maybe it's that vortex and that in the image. At a Stokes number of near 1, because these are phase locked, there's the same vortex right here. And you notice there are no particles in the vortex core now. The place where the mixed fluid existed without two phases is now the place where there's been demixing. The particles have been centrifuged out of the vortices. And if you were building, for example, a combustor and injecting liquid fuel droplets, or you had any other two-phase flow in which there was turbulence, expect to see the vortices for which the Stokes number is 1 to be devoid of those particles. There are centrifuges that, ironically, make the turbulence demix the fluid. In conclusion, as you already know, turbulence is everywhere, and I hope if you didn't already know it, I persuaded you it's so beautiful and very hard. All turbulence models are based on wind and water tunnel and water tank testing, and they all use at high Reynolds number some kind of interpolation or French curve between nearby, one hopes, nearby data points. And because of that, there's going to be a continuing need for wind tunnel testing, and I applaud your new icing tunnel here. Thank you.